you have to know the rationale behind why you have to use the feature selection. So there are several types of feature selection techniques or methods. The first one is called the filter method. Now, the filter method uses statistical tests to rank the features. A good example of the filter method are correlation. And I think in our previous classes, you must have seen us did a correlation heat map. Although I didn't tell you guys why we did that, much like that. But somehow then what I was looking out for is to see if there were potential multicollinearity existing between the features. Although we were not prioritizing feature selection because I knew I would have to take it as a separate class, and then we could go into, when we go into the practicals, you could begin to see how we could use these approaches to screen features. So the correlation is one approach we use in the filter method. The second one is chi-square. Now, why? Someone will ask why chi-square? Because chi-square is quite very important in establishing relationship, especially in categorical variables. So because of the relationship we use to build using some of these approaches is very, very important. And also chi-square has a matrix that we could be able to use, for example, to see are these things statistically significant or not. The features that are slightly statistically significant at certain confidence interval, for example, those features, you wouldn't throw them away. Rather, you would have to keep those features in your model. So chi-square is a very good approach in filter method. And then we have the mutual information gain. So the mutual information gain approach also is a very interesting approach that we use to know the amount of entropy that that particular feature have been able to contribute. So, or randomness, the degree of randomness we observe. So that help us again to see if we could rank this features based on that particular criteria, and then we could select them. But one thing I want you to understand is that in the filter method, ranking of features is very important. So you rank them based on the statistical test. Like I said, a very key criteria could be that you're looking at the p-values. Are these features statistically significant or not? Then you could automatically drop them. But again, a feature is important, not necessarily is statistically significant. So because some people may think, oh, the features that are not statistically significant, okay, let's throw them away. No, it's not mathematically sound. So what you do is after you perform this statistical test, you need to rank them. So it is that ranking that helps you to build up like a cutoff. In the case of correlation, for example, you will see this tradition of saying if the correlation coefficient is more than 70 or 80 percent or 0.8, because correlation is measured from from -1 to 1 or 0 to 1 in some cases. So if you looked at the correlation score that, oh, these features have a correlation coefficient score of, let's say, 0.88, that means these features are having strong correlation among themselves. So it doesn't make sense to keep the two of them. You could decide to pick one and leave the other one. So, but again, you will need to rank them. So by the time you rank, you can say all the features that are having 0.8 above, remove them. Because in the case here, correlation is the problem. If they are correlating among themselves, you cannot be able to keep working with them. They are struggling. It means they are competing with each other. So you have to find a way to do away with those features. Not doing away with the two of them completely or three of them completely, but rather you could find a way to select one of them and keep the other ones out. Now, because this means the two of them are similar. They are doing the same thing. That's what we're trying to say. Likely the features that are doing the same thing, you will see correlation among themselves. So there's no point keeping them, you know. So correlation help us to be able to determine that. And then, like I said, the chi-square too. So an example of this filter method is removing features with low variance. So when we enter the hands-on section, I don't know if we could do that in today's class, but let's see how far we go. You would see that things like VIF is a very good approach of helping us to filter. You use VIF to determine cutoff, to measure these issues that has to do with the low variance. So you remove the features with low variance. And remember, I showed you in the previous slide what the low variance means. If you remember when we were talking about the underfitting. Good. So that's what we're trying to say. So you could filter out those features that you notice they have this low variance out of it. And those ones, like I said, with high correlation, you could find a way to remove them. So the second method is the wrappers method. Now, like the name talks about wrapper, Anyway, I will talk more detail about them in the subsequent slide. So the wrappers method uses a model to evaluate the future subset, e.g. the forward selection and the backward elimination approach. I like some of the graphs I used to get from this wrappers approach when I use things like the forward selection and backward selection. But I think I would okay. Let me keep the other things to myself and talk about them in subsequent slides. So the wrappers method for forward selection is a good approach. The backward selection is a good approach. A good example is the recursive future elimination method, RFE. Then there is the third one called the embedded method. So the embedded method is that approach of future selection that is performed during training of the dataset. Now, a good example is the lasso regression and tree-based method. If you remember in our last classes, we talked about logistic regression, and then under the parameters that we were defining, you will see where we use C and then we use L1 when we were talking about hyperparameter grid search. We were putting some matrices in the features. Well, maybe I could show you guys some of these things in the hands-on section. So usually we embed, that's why it's called embedded method. We embed it inside the models themselves. So if we are using things like decision tree, we could decide to tell the decision tree to use the features that are most informative. And then we could also decide to prompt it by trying to cut off the tree, maybe around 3 depth. And say, okay, we want the depth to be just 3. And then we also want you to work with the most features that are informative in our dataset. So that's what the embedded method does. You put it inside the model during the training. So you can see the name, embed, you embed it. So you don't really use it as a separate entity. But again, some person could use it as a separate entity. It doesn't matter, but most of the time we put it inside the model. Then there is another one we call the hybrid method. Now, you can see the hybrid method. It means that it is combining 2 or more methods of feature selection. The hybrid method can combine, for example, the filter method and the wrapper method to select the final features. It could combine maybe the filter and the embedded method to select the final method. I think for me, I use the hybrid methods a lot. Sometimes I don't even care to know the name, but I use it a lot. First I use the filter method, maybe select K-best, for example, to select maybe the best features. And then next, I would use things like lasso in my model during training and find a way to shrink them also, stuff like that. So the hybrid method, it's you could combine them, and then there are times you could even use the three, the filter, the wrapper, the embedded, combine them all in one go. So, but again, sometimes it's not just to be a sort of an addict to, no, like you have to have a reason why you use this thing. So it shouldn't be like, oh, I just have to use it. No, always try to have a reason why you want to use that. Then we talk about the assemble method. The assemble method creates a sort of a consensus score where the importance of each feature is the result of the combination of the individual feature selection method score. So again, I have used the assemble method during my work in during my PhD in like I said, remember if I when I told you guys earlier on that after the first screening we had like 2,000, 1,500 futures. The next thing we did was to use this assemble method to train random forest XGBoost. So when we train them, at each goal, we save the future importance. We save the future importance. We split the data set into stratified k-fold. So when we split them into stratified five-fold, at each training of each of this fold, we save the futures, the future importance score. So by the time we did that, we came back and aggregated. We created this CSV file where we have the future selection from fold one, future importance from fold one, future importance from fold two, fold three, fold four, and five. Then we now told ourselves that why don't we focus on features that are most consistent across the five-fold? So consistent in this case are the non-zero supports across the five-fold. So each of the features that have non-zero feature importance score, we've picked them. And that was how we had the 16 of those features. But we didn't just settle for random forest alone. We did the same thing to XGBoost. We noticed it was still these features that were popping up. And then we say, okay, fine. It shows these features actually have strong signals with this tech score. But however, you have to be mindful of what we call hacking. You don't, be very careful so you don't, in other words, trying to make sure your hypothesis fit into your assumptions. You just the whole aim of research is you don't know the results. You want to discover new knowledge and new things. So sort of that. But the embedding help you to at the end of the day you come up with the scores you use. So you could decide to use filter method, for example, and then you use wrappers method, and then at the end of the day you aggregate them and say, okay, which of the features are always popping up? They are consistent or something. And I say, okay, these features seems to be the best features. Let's work with them. So that's how the embedding, the assemble methods works. So let's look at this future selection methods individually. We have highlighted them. Let's try to focus on them more closer. We said that filter method is statistical based because you perform some statistical score. Remember? Sorry, I don't know. Do you have any question? Are we all together?
Yes.
Okay.
What
Good.
the question that's running in my mind is in the feature selection method, one of the things you were talking about is also it enhances or reduces computational efficiency, improves computational efficiency. Now, and then it helps in accuracy. But then, is it also possible to say the features you are selecting from is not as if they are noise, but there might be relevant feature. Is it possible that you reduce okay, I have 1,000 features, those 1,000 features, they are very important. Okay, but probably you are trying to make an experiment against a baseline experiment, and then the person also used maybe 500 features from that work. And then you decide to, okay, in order to make to compare effectively with it, I have to adopt 500 features, but not that the rest other features are noise. But I'm trying to adopt certain amount of features in order to correlate with what he has already. So in that kind of case, does it give a false, accurate, will that affect the model accuracy because you have left some important features behind? Or well, I'm not sure, is that possible? And if it is possible, will it not affect the accuracy of the model because you have left some features that are important behind? You chose to use a subset of the feature, not necessarily because they are not important, but because you want to help your computational efficiency, and then you want to compare with a particular baseline model.
Yes. So again, everything bounds back to the aim of your research. Now, if accuracy is an important metric in your research, then you will always find a way to have this optimal accuracy score. So irrespective of the features that you have. In other words, for me, I think the first approach I'm going to do is to test with all the features first. So let's say you have 1,000 features. I'll first of all test with all the features and know what is the accuracy score when I put all of them. Then by the time you see the accuracy score, you now begin to say, okay, is there a possibility that if I have a reduced feature subset, I can still have an accuracy score the same as this baseline accuracy, or even more than the baseline accuracy when I have all the features together? So that's now where these feature selection methods will begin to come into play, because they will now begin to help you to now narrow down your search on the most important features. For example, you want to do research on understanding maybe HIV prevalence in let's say Southern Africa. Or it means all the South African countries are important to you. But the question is, do you have the capacity, the resources to, pull all the information or sample all the people in South Africa? No. So the next thing you need to do is to say which countries in South Africa it's more important for me. Now you begin to do things like sample size. You don't say, okay, let's do some sample selections, and then you come up and say, okay, 3 countries, it's fine. Then these 3 countries, is it possible to sample everybody in that country? No. The next thing you said, okay, let's look at some age range. And I said, probably we could focus on 40 downward, maybe to 15 years. So by the time you create that niche, the next thing you need to now tell yourself is which region of the country do we have to focus on? In that country, we need to focus on. For example, in Nigeria, that we have 36 states, you may say, oh, it's impossible for me to focus on the whole 36 states in Nigeria. Why not we pick some few states, maybe 3 states from the middle belt, 3 states from the west, and 3 states from the south, and then at the end of the day, we could be able to, this could give us an equal representation of all the other 36 states. So most of the time, when you have the ground truth, the next thing is to now begin to find a way to optimize your system, to find minimal features that could give you optimal score. Is anything. So what you just said again, it means that domain knowledge is playing a very key important thing in selecting the features. And as we go further, I will talk about how the role of domain knowledge is very important in selecting features. You don't leave these things just to the mathematical algorithms to do that for you. You also have to know that there is a place of the experts. The experts could also guide you in identifying these features that are most relevant, because there are situations where you would see a feature that it's already established in literature, But now you may begin to find that when you're testing that future, trying to do the future selection, it's not picking that future. Maybe it's completely moving away from those futures. And then you could, by your mathematical intuition, say, oh, that feature is not important. But the domain experts may come and look at it and say, no, I want this feature, I want this feature. So you have to work collaboratively with the domain experts to identify the final feature subsets that are important for you to work with. So I don't know if that answered your question. Okay, great. So filter methods, like we said, it ranks the features and select the features based on their statistical relationship with the target variables by helping us to remove irrelevant or redundant data from the model. So remember I said we perform some sort of statistical test, and then we rank the features, and then we select them based on a cutoff. So for example, it looks like this. Let's say we have these features, 1, 2, 3, 4, 5 of them. We perform statistical tests, and then we rank these features where we have 1, 2, 3, 4, 5. And then we discovered that, okay, based on this feature ranking that we have done, these features, maybe 1 and 2, or these 3 features are the best features based on that cutoff. So we select only them. So you first of all put all the features in that particular data set. And then the next thing is for you now to do this correlation chi-square or the mutual gain approach. And then the next thing is to rank them, and then you select among them the best features. So then you could remember we said the features we are removing in this case are those features with what? Low variance. They are the features with low variance. So take note of that. We're not just removing features, but the ones with the low variance are mostly the features you are removing, which means in correlation terms, it is those features that are having issues on multicollinearity. It means the two of them are highly similar. So we begin to say, no, we don't need those features. And then we do away with them. So we said the filter methods are fast, they are model independent, and they improve the computational efficiency. However, the setback of this feature selection is that they overlook future interaction. So when you now have a study that causality is crucial, this feature selection approach assumes that independency, because what is correlation? Correlation is simply the relationship between one or more features. So this features means it's a one-to-one sort of relationship, but that doesn't really add up in the real world. A lot of time in the real world, correlation is not causality. So because correlation is not causality, you cannot just because the features are correlating together, then you just determine which features goes in and which features goes out. So we must be careful when we are using the filter method, because it comes with that notion that the features are independent. It's a one-to-one relationship. It doesn't look at the other baggages that are capable of happening. Because, for example, I told you guys in the early classes we had last time that imagine when you're carrying out a research to determine the cause of death in people with lung cancer. And then you have features popping up like smoking, you have age, you have other environmental, and probably you also have things around family history or medical history and all that. And then it's obvious, it's easier for you to see people with smoking dying more from lung cancer. And then you could easily conclude and say smoking causes lung cancer, but that may not be true. When you now zoom into it to understand what's happening, you now get to discover that it's not really what's causing it, but the smoking was triggering an underlying condition that was actually causing the cancer patients to die. But if you don't zoom in to understand what is triggering, you could easily conclude at the surface and say smoking causes death in people with lung cancer. So you see the problem. So this causality is being ignored because of the correlation that is making you to judge that this relationship already means this, without forgetting that the correlation is talking about independency, while causality is talking about dependency. So these are two terms that you have to be mindful of as you continue your journey. Because even in finance, it's easy for you to associate indicators like poverty with economic status or something. But maybe there are some underlying conditions that are triggering it. Maybe this poverty, the reason this person, this area is associated with poverty is because of maybe conflict. And now the fact that, for example, I see a lot of people make assumptions, and sorry, and I have to say this, growing up in the North as a child, you have this notion about somebody from the southern parts of the country where they associate them with lots of things like rituals and all that and all that. So there is that um, inherent bias that is already built, and then that lack of trust between them have been already established. But that's not true. You find out that when you grow up and you begin to mingle with somebody from the south, you discover that not all Southerners are like this. But because of the small uh, contaminations inside them, or the bad eggs, have already ruined the whole or generalized on everybody. So this whole thing we have to treat when we are dealing with filter method, we have to treat everyone based on one-to-one relationship. But in real world, it does not happen that way. There is future interactions that do happen, and that's one critical setback of the filter method. So we said the advantage of the filter method is that it is fast and inexpensive. It evaluates the futures without the training model. Remember, because you pick the target variable, associate it with the independent variables. So it's very, very easy for you to quickly run through it without having to go through this period of recursions. It helps you to remove redundant or highly correlated futures. Like I said, you would be able to visualize quickly through a heat map of the correlation to see what sort of relationship is happening and to see which futures are struggling with each other. And then you could be able to remove them out. So, like I said, the limitation is that it does not consider interaction between the futures and potentially is missing out this important combination. Like I told you guys earlier on that when I was working on this 25 subset of these biomarkers, I have to perform some sort of combinatory analysis to identify the best future subset. So because in that kind of situation, I could not really, I could not just focus on association alone, because association is more about relationship coming from things like correlation and statistical tests. If I do that, I would be able to ignore that interaction that could happen in these biomarkers. So, but when I did that combinatory analysis, which is more like a flipping, you put everything together, you combine them, you mix them up, you flip them, you turn them out. So just like in probability, where we said we'll flip a coin, so it's similar thing like that. We did this combination and permutation, and then at the end of the day, you come up with a future that includes, for example, urine biomarkers, that also include blood serum and plasma biomarkers, but not just one set of biomarkers that you're getting just because of association. So that combinatory spice that could help you to really identify most predictive features, you should not just ignore it by settling down only on the filter method. But in a situation where you need to prioritize the computational resource and you want it quickly, then I think the filter method is not bad. But again, like I said, do not forget the place of the domain knowledge, because that helps you very well as well. So we said the common example is the information gain. It measures the reduction in the entropy to assess the future importance. And as we start the hands-on, you will see how this all works, and we will do them together, and you will see how we arrive at these futures. And then we talk about the chi-square, which evaluate the relationship between categorical variables. Remember, when you want to look at, for example, gender associated with educational level or something, that's a categorical variable. So it makes sense if you testing like using a chi-square approach. There is the Fisher's test or the Fisher's score also help us to rank these features based on some discriminative power. And we also talk about the correlation coefficient. It could, and again, when we talk about correlation, remember correlation is not just quantitative. It's sort of, it's also kind of qualitative. Also, we have the Spearman ranking correlation, we have the person correlation, and then what's the third one? I think it's that one escaped me probably. But we have two major ones: the Spearman ranking and the person. So the person correlation talks about quantitative variables most of the time. So you just focus on quantitative, and it assumes normality. Okay, it assumes normality. So when you're performing it, always know it talks more about normal distribution stuff. So the person correlation on sorry, the Spearman ranking on the other hand focus also on quantitative, but in this case it does not assume normality. So when you're looking out for deviation from the normal distribution pattern, then the Spearman ranking makes a lot of sense for you to be able to use. Because when you're talking about categorical variables, you don't really, they are not something you could quantify. So you cannot use qualitative. So qualitative now is where you now begin to think about using things like chi-square. I don't know if you understand the method. So, but when you have quantitative variables like height, like age, and maybe salary as well, something you could quantify, then correlation is the good option. Then you now begin to think about how this, you don't just make assumptions, it's normal. So maybe from your visualization from exploratory data analysis, you must have seen how skewed some of these variables we're looking at. So that could help you to determine which of the correlation you could do. And I think the Spearman starts from -1 to 1, but normally they are not really that different as such from each other, but always take note of the correlation approach you use. Then we have the variance threshold, which I think is the VIF approach that I talk about, and we'll look at it during the handout. It removes the low variance futures under a set of threshold. And then we talk about the MAD, which is the mean absolute difference. It's similar to the variance threshold, but without squaring. Of course, we most times when we talk about absolute, you already know, it's just you put them under this. Remember the last class I showed you guys how you put those things. And then we have the dispersion ratio. So it uses the ratio of the arithmetic or geometric mean to identify more relevant futures. But I think in all this, the most popular ones that I have seen and used in the course of study, because we wouldn't be able to look at all this during the hands-on section. I think it's information gain, chi-square, and also correlation, coefficient and variance, VIF. I think those were the ones I have used a lot. during my course of study. Now, in detail, the wrappers method. Remember, we said there is the wrappers method, which is the model based. Okay, the wrappers method, which is the model based. So, what the wrappers method does is that if we have this pool of features 1, 2, 3, 4, 5, we build the model and then we feed the model recursively. For example, you take the first three, you feed the model, you output it, you see which of them, you see the scoring, how is the performance of this three. You take another ones, you feed it into the model, you see their combination, how does the performance looks like. So it does that using a model. So you build a model to be able to identify the subset. You do them that recursively, or you build it iteratively, you iterate between them. So that iterations that you do helps you to select the future subset by training them and evaluating them. So if you take the first two, for example, you check their performance, you go back again, you see you evaluate, you train them, you check, you evaluate. You say, okay, this is the score when I have just two features. Now let's take three. You check again with three. You keep their score. You take four. You take five. You continue to do that until you have 100. So you move from, let's say, two, you see, you move from three, you see, you move from until you say, okay, now let's take maybe the whole 100 futures. Okay, it's fine. So now when you now have 100 futures, so but again, you could do that in a forward approach, selection approach, or you could do that in a backward sort of elimination. So the backward means that you start by going, coming from back. So you have 100 features, you begin to drop them. You begin to drop them. You said, okay, what happened when we come from 99? What happened when we come from 98? What happened when we come from 90? Stops like that. So you come back via the backward approach. So you come back and eliminate. While the forward selection means you start with one, you put another one, you put another one, you put another one, you put another one. You continue to put recursively. And then if you're coming back again, you drop them recursively. I don't know if you understand the pattern. So you can come this way or you can come the other way. So good. So you do that until you find the best combinations. So it's a very interesting approach. So he said, stop when the performance no longer improve or a predefined number of futures is reached. So you consider that approach until you notice you don't get any improvement again. And then, you stop. Because if you have 100 futures and you're coming from backward and you notice that at 60, nothing moves again, then no need of going to all of them. You just say, okay, these 60 features, you work with them. If you are coming maybe from forward, you have 100 futures, and then you discover that at 50 or 60 futures, you are fine. Then there's no point about putting them. So it will consider putting them in a forward approach or in a backward elimination approach. It's depend on what you choose. So the niceness of this, or the interesting thing about this, is that it helps you to find the optimal feature subset for a given model. Very nice, because you're looking at all this combination. It's forward, it removes, it eliminates, so it really keep doing it until it's fine. But the problem is it's computationally expensive, especially for large data set. So I think that's one of the problem I talk about whenever I'm dealing with the wrappers method. I wouldn't want to, if in fact when you begin to have large data set of maybe 30, 50, it's even kind of difficult because it's very, very computationally expensive because it will go, you trade, come back. But again, these days, if if you notice that feature selection is very important in your project and you have the computational resource like GPUs, then I would say go for it. It's not a big deal. They could take maybe weeks, they could take days, they could even take hours or minutes, but it's worth trying because that will save you that whole issues of having to struggle if the model is going to be fine or is not going to be fine. Because the wrappers method will really help you to identify the optimal features that you need. So we said it improves the model performance by selecting features in the context of the model. It captures feature dependency and interaction. So that's another beauty of it because it looks at all these features and see how they are relating and interacting with each other. But again, the major issue with this approach is that it is computationally expensive, especially when you have a large data set. Now, when we say large data set in this case, we are not just talking about only the features in this case. We're also looking at the samples, okay? So imagine if you have 1,000 samples. It will not be the same when you have just 200 samples. So we're talking about when both the sample size and also the features are very large. That's one of the issues. So the forward selection starts with no feature. It adds one at a time until no improvement. The backward elimination, on the other hand, starts with all the features and remove the least significant feature iteratively. So you see, it makes sense. So anywhere you go, you can come from the back or you start from the forward approach. So then the recursive feature elimination approach eliminates the least important features step by step until the optimal subsets remain. So any of them that you want to use, for me, when I'm trying a very important project and I don't have more than let's say 100 features, I used to try the wrappers method. And what I do is I don't just search it for one approach to forward alone. I will do the forward, I'll see what I have. I'll do the backward, I'll see what I have. I'll do the recursive, and then I'll see what I have. Then I will now settle down and say, okay, this is the final future subset. I don't just do one method and say, okay, it's fine. Because if you are with the panel of experts, most of the time they will ask you this question. Why did you also check via the backward elimination approach? Why do you just settle down for one method? Then you could now be able to say, oh, I have checked, by the way, but I discovered this method was the best. So that's why I settled for it. Than to say, no, I didn't feel like. You didn't feel like? So you have to show them that you actually did a good job, a thorough job, by not just focusing on one thing alone. So, any question on the wrappers method? Any no question? Okay, great. Okay, fine. So let's move to the embedded method. So we said the embedded method is also called the integrated into model. Remember, I told you guys that during model training, we put it inside the model, if you remember. So we said we perform the feature selection during training and combine filter and wrappers methods benefits. Then more efficient than wrappers method, and also it often scale better to large data set, which is true. And all this I could actually testify about them because I've used them. I've used the lasso to see how it performs. And I remember when I had that 1,500 features, 2,000 features I told you about, the lasso really helped me because I used it to see how many features will I have. And then at the end of the day, it shrink them, I think, to around 600. And then that 600, I used ElasticNet to see what will I have. ElasticNet gave me, I think, around five something, I can't remember precisely again. And then I used ridge regression, but the ridge regression is not going to shrink it to zero, but it's also helpful. So it's a very nice method because it's scaled better and it's faster compared to the wrappers method. So a good example of this technique, then it works well with specific learning algorithm, but may not generalize across all models. It's true. I think very, very nice when you're looking out for normally we integrate them more into regression-like kind of model. Things like least square regression, because they are more looking like the regression family. So we put them in those kind of decision trees. We put them in logistic regression. All these sort of linear, generalized linear model families. That's where we usually use them a lot. So it's not all models that you could use them. But the beauty again is that I think most of the model you could be able to use them. If I'm not mistaken, I think the support vector machine do have the property. But again, even the support vector machine, it's also looking at the family of the regression, so it's not really that far. And also, even in neural networks, you could also see we use them as well to help us to reduce the future. So a good example is the lasso regression or regularization 1. So the L1 regularization shrinks the coefficients, removing the less important futures. So what it does is that it's kind of help us to shrink them to 0, so that the futures that are having coefficient of 0, we just forget about them and focus on the non-zero coefficient. So the lasso is very, very interesting approach, because most of the time you can play around with so many matrices. You don't have to use the default that comes to the model. You could try different metrics and say, okay, what happened when I tweak the metrics like this? What happened when I increase the entropy? What happened when I do this? So you could actually play around with the tightening of the regularization belt. Okay, so you can check what happened here. What happened if I loosen it? What happened when I tighten it? And stuff like that. So it helps us to be able to identify these less important features and we remove them. And then the decision tree random forest also fall into this family of the embedded method. Remember, because I told you we could even combine them into a hybrid by building the lasso inside the decision tree itself. And then at the end of the day, we focus on the features importance of that decision tree random forest. So we select features based on the node splits. Remember we talked about in our last class how we could easily split them based on the information gain. We call it the Gini, the entropy. We split them from the node, and then we have the decision the individual trees. We continue to split until we have no further information. So I told you guys that one of the things we could do in we could help to trim the trees, because when we leave the trees, it could be so boring and the interpretation becomes complex. So sometimes you would just say, I just want the first 3 depths. So you say the depthness of the decision tree or the random forest should just be 3. So it means that what you are telling it is that after the node, the root node issue, when it did the first split, the second split cut. So sometimes you could say, I want the 4th depth. It means the root node, the first split, the second split, the 3rd split, then you cut the 3. So things like that. So the splitting is based on the features that has that impurity of the gene or the information gain. That's how we determine it. So in another word, it's like you have the features, you put all of them in the model, and then you do them. It could be the lasso, it will shrink them. For example, in the lasso, remember it shrink. So all the 2 features have gone to 0. You have these 3 features that become the final feature subset. If you are using the decision tree or the random forest, like I said, you could even pick this lasso, put it inside the decision tree, which makes it like a hybrid. And then at the end of the day, you feed the features, and then you have the final features. So you see, it didn't make sense because it's going to be faster. The decision tree models actually train very fast compared to these other future subsets. So it makes sense a lot because it will help you to prioritize the features quickly without having to go through that rigor that the wrappers method will take you through. So a good example, XGBoost, for example, under the gradient boosting family, can help you to identify these features with which reduces the model errors the most. So it's a very, very nice approach that I use it a lot. And even one of the tasks I'll show you guys, we'll do together during the handout. You see how we could utilize it a lot, you know. Then we see how to select the right feature via feature selection methods. Because most of the time, the question that comes to your mind after hearing this is, now that I've heard this, how do I now use the right method? How do I go for it? So we need to talk about that. So the first thing is to look at the dataset size that you have. The filter method works best for large data set due to efficiency. So if the data set is so large, imagine when maybe you have million sample instances, you have instances, and then maybe you have 1,000 features. You know, it wouldn't make sense to think about using the wrappers method because it would take years or ages to get the features. So you have to focus on the one that is faster and could be able to save your resource. So look at the size of the sample size of the data set, and then that could help you to identify which method you should use. The second thing is feature interactions. Are feature interactions very important to your work? Is it something that has to do with causalities? Do you want to know how these features are playing around, combining with each other? If so, then you should prioritize the wrappers and the embedded methods because they will better capture the complexity in the relationship. Remember the filter method, they are more like linear because they just want to look at statistical relationships. So it wouldn't make sense if they have that assumption of independency, but this other one, could help you to evaluate or capture that relationship that is existing in the data set. So the future interaction is also another thing that helps you to know what sort of feature selection method you should use. Another thing is the model type. Some techniques are specific to certain models, e.g., lasso for linear models. Like I told you guys, the regression family. So it's kind of, you have to think that direction. So if you are using things around that regression family, then if you're using embedded methods, something like lasso is fine. And then the decision tree types for decision tree based models. So like I said, if you are going to be focusing more on maybe like a classification problem, then you could even put the lasso inside the decision tree model like random forest or simple decision tree. And then at the end of the day, you filter, you select the features, and then you move on. So example with it, use filter method, e.g. correlation, variance, threshold, VIF, to quickly remove irrelevant features in high dimensional data set. So when you have a large data set, that are high dimension cases, then you could quickly use the filter method to, do the initial filtering. Then if you are maximizing the model performance, that if the accuracy in this case is the priority, then it makes sense for you to explore the best combination that gives you the optimal accuracy score. So the wrappers and the embedded method in this case will become a very important thing for you to look at. For example, you could consider looking at embedded method like decision tree or even lasso, and you could look at wrappers method like the recursive elimination, forward elimination method also, the RNF and the rest. If you look at them, and then you could now determine how your model, your final future success should look like. So the major key takeaway here is selecting the right methods improves the accuracy and reduces overfitting and make the model more interpretable. So you should consider these things when you are choosing the right feature selection method. However, there are best practices. So what are the best practices? Avoid removing too many features. Because you may lose information. You will lose information, not even you may. You will lose information when you remove too many information that retain enough. When you remove too many features, you lose that feature that has information about the target variable. So do not say because of feature selection you want to remove everything. No, always make sure that you are careful and have a reason why you are removing the feature. Make sure it is really features that are redundant that you are doing away with. Check future correlation to prevent redundancy. Like I said, that future correlation really helps you, especially when you visualize them on a heat map. You could easily see how the multicollinearities are happening. And when you notice it, you can now, go in and say, okay, these features are competing with each other. Can we do something about it? Then again, I talk about use domain knowledge for better future selection. So this part get back to the question that Monday raised earlier on. The domain knowledge is very important. From literature, you will begin to see these things. You begin to see how these features are very crucial when it comes to determining, for example, certain medical condition. So it won't make sense for you to remove those features. So the domain knowledge informed you ahead of time about these features that you should keep and the features that you should do away with. And also consulting the experts in the field. You will talk to people that have done this similar kind of tasks. You could hear their views. They could help you to prioritize these features. There are what we call the knowledge graphs. You could build these knowledge graphs where you could be able to really see how these interactions are happening, how these are connected, the dots are connecting, and then you could be able to use those things to be able to filter out these features and identify those ones that are more relevant. So that's why most of the time, in some tasks, you see a lot of time is spent on building the right features, on selecting the right features before talking about building your model, because the model is very, very easy. The algorithms are there for you. But the processes you arrive to get the final models that you fit your algorithms are very, very crucial. So you shouldn't just be in a hurry to build models. Rather, try to understand the process. And that's what the domain knowledge does for you. The literatures that you get to read, you are not reading them because you want to just copy and paste them on your research. No, you're reading them to understand what has been done before now, what has been identified, and how do you also contribute to the gaps that are in knowledge. So that's why you study the literature to get this information to help you to be able to do something different. So use domain knowledge for the future selection, then validate the performances using cross validation. Like I told you earlier on how I use the stratify fivefold approach. That way, I was able to see these features, how they are consistent across the fold. So you don't just you try to validate these features, and then that way you could be very sure that these features that I selected are actually the best features. They are not just I'm not just selecting them based on some sort of impression that I saw from one time approach, but now I was able to validate and see that these features actually they actually generalize even in the testing set, because the cross validation, remember the leave one out approach where you have the 4 parts, you could use them, for example, for training, and the 1 part you could use it for testing. So it's similar thing. Does these features you select, do they generalize well in the training set? How are the errors? So you look at all these performances to be sure before you build the final model. I want you to know that machine learning, AI, artificial intelligence, it's about exploration. You are exploring. So it is not just a science, it's an art. And anything that has to be an art, it has to do with crafting. You have to be a very good crafter. You have to be a very good storyteller, because you are telling a story. So nobody could tell it better than you. So because of that, you have to make sure you put all the smaller pieces together in order to tell a very good story. So make sure that you are able to validate these features, that they are actually the best features you are using. Then we talk about always experiment and validate the future selection choices. don't just settle for one feature selection choice alone and say, oh, this is fine. Explore other features and see their angle to see. You know, one of the problem again about research, most of the time, people are scared of criticism. But this criticism is to make you better. It's to make you to become a better version of yourself. So be open to some of these approaches so you could be able to have more room for discussion and robust engagement, because that's where the best comes out. By the time you said, I did it like this, I did it like this, and someone could say, oh, but you could have done it this other way. You know, so that person opened up another bubble. And because of that, you could now begin to talk about this from a newer angle. And you know, you say, oh, now I have a piece I need to come and put in the puzzle to actually make it fit better. So with that, I think we've come to the end of today's class. If you have any questions, so you go ahead and ask.